previous section, we understood how to calculate coefficient of lift from coefficient of pressure value. So now we will try to understand how to calculate the coefficient of normal and axial force from the value of coefficient of pressure. So in the first equation, as you can see, it is the coefficient of normal force, which is equal to 1 by c, that is the chord length, and the integral from leading edge to trailing edge, coefficient of pressure on the lower surface minus coefficient of pressure on the upper surface in the direction of x, plus the coefficient of frictional force. See what normal force and axial force consists of: pressure force and the shear force. So the first term in the first equation represents the coefficient of pressure due to pressure force, and in the second term of the first equation represents the coefficient of frictional force, right? That is Cf on the upper surface and Cf on the lower surface. And similar analysis goes for the calculation of coefficient of axial force, right? Very important term called as center of pressure, right? So all of you know center of gravity. What is center of gravity? It is a point at which all the mass of the object is assumed to be acting at, right? So if you hold any unbalanced structure such that it balances itself, it don't fall, or in other words, in engineering terms, if the moment is zero, that point is called as CG point, right? So center of pressure is analogous to the center of gravity, right? Only difference being, here the center of pressure is the center of the entire pressure distribution on the upper surface and lower surface. It is the CG of the area under this pressure curve, right? So that is center of pressure. So if you see, I have two diagrams, one on the left with low angle of attack and the one on the right with high angle of attack. If you observe carefully, the position of center of pressure is changing with change in angle of attack, right? So the moment I change the angle of attack, center of pressure changes, because the reason is, let's say I increase the angle of attack from 2 degrees to 5 degrees, right? So what happens when it was at 2 degree, there was pressure distribution based on the velocity. Now if I increase it to 5 degrees, the pressure variation changes because velocity is changing. The high pressure region come towards the leading edge, hence pulling the center of pressure towards the leading edge, right? In an area when the majority of the area is towards the leading edge, so the center of pressure point is towards the leading edge, right? So in other words, as the angle of attack increases, the center of pressure point moves towards the leading edge. Now, if such a point exists, if center of pressure, if I consider in my analysis, it is very difficult to arrive at certain conclusion whether how much lift is generated at each and every point, right? It is very difficult to analyze. Why? Because the position of center of pressure itself is changing, hence changing all the moments. Now to understand and analyze the aerodynamics of airfoil better, we define another term called as aerodynamic center. I define this aerodynamic center keeping in mind that center of pressure always moves. So it is very difficult to track a moving point. So what I want in aerodynamic analysis is a fixed point. Aerodynamic center is a fixed point about which the moment exists. When you change the angle of attack, lift force changes, but the moment remains constant. Hence, dCm by d alpha, that is variation in coefficient of moment, with respect to change in angle of attack, is 0 for aerodynamic center. Whereas, compared to the center of pressure, where the moment keeps on changing, but the rate of change of moment with respect to angle of attack was constant there. But in this case, the rate of change of moment is 0. Means when you change the angle of attack, the moment doesn't change. And the second important characteristic of aerodynamic center, it is fixed. It does not change with angle of attack. Now, if you could able to recall, in previous lectures, we discussed something about quarter chord point, right? So what this quarter chord point is, it is the location of aerodynamic center in most of the cambered airfoils. We assume that it is at around 25% of the chord, so that is nothing but the quarter chord point. Now I just want to give a quick glance about the Mach number. Mach number is the ratio of velocity of an object to the velocity of sound in that environment where the object is moving, right? So it is given by the equation m is equal to v infinity by a, where a is the velocity of sound in that particular environment. So I can expand a as under root of gamma into r into t, where gamma is the ratio of specific heats, that is Cp by Cv, r is the gas constant, and t is the atmospheric temperature in that environment, right? So if I know the temperature of the altitude, at any altitude, if I know the temperature, I can calculate Mach number. Another observation here is the Mach number on the Earth's surface is not same as at higher altitudes, right? So you can do the homework, you take different temperatures and try to calculate the Mach number for the same velocity of the object. The result is very interesting, right? You just check it out for various temperatures, what all the Mach numbers you get, and discuss in the comment section below, right? So in order to differentiate various Mach numbers, there are certain ranges we consider. Let's say, for example, subsonic, I call all the Mach numbers below 0.8, right? If an object is moving at, let's say, 0.7 Mach, I call that speed as subsonic. And if the Mach number exists between 0.8 and 1.3, that is a transonic region where the speed is getting transition from subsonic to supersonic. Now, one Mach number where the speed of the object is same as the speed of the sound in that environment, then that Mach number is called as sonic Mach number. And beyond 1.3, I call it as supersonic, and above 5, hypersonic, and about 10, hypervelocity, right? So just to give you a glance, just to give you a rough idea what this Mach number range means, for Airbus A380, the maximum cruising speed, maximum cruise Mach number is 0.96, right? If you can able to imagine, so Airbus A380 can move at 96% of speed of sound at that environment. So that is its maximum velocity. Compare it with some fighter aircrafts like Sukhoi Mk-30 or F-35, which can go at Mach numbers 2.53. That means those aircraft can fly at supersonic speeds, right? At 2.5 times the speed of sound, right? Just to give you an idea, when a train approaches you, suppose you are standing in a platform and the train approaches you and the pilot uses horn to indicate that the train is coming. You could able to hear the horn because the train is traveling at a lesser speed compared to the velocity of sound. Now imagine a situation, the train is moving at the speed of sound and the pilot pushes the horn. Can you able to hear the horn? I want you guys to pause this video right now and think about it. Tell your thoughts in the comment section below. Now in this case, when the velocity of train is same as the velocity of sound and the pilot pushes the horn, we can't hear the sound on the platform until the train approaches. Train is exactly in front of you, you can't hear the sound. Moving on to the extreme end, let's imagine that the train is moving much faster than speed of sound. Can you able to imagine the scenario? In this particular case, of course, when the driver pushes the horn at certain distance from the platform, we cannot hear anything. because the train itself is moving faster than the speed of sound. But even the train comes next to me, in front of me, I cannot hear the sound because there forms something called as Mach cone. So all the sound waves forms a Mach cone. So in this particular situation, the moment train is past me, then only I could able to hear that the driver has pushed the horn. Moving on to hypersonic aircraft, so we have Blackbird, lot of aircrafts, experimental aircrafts of course, developed by NASA that are in the hypersonic range, which is above 5. Right? Now this hypervelocity, that is a Mach number greater than 10, that means the aircraft is going to fly 10 times the speed of sound. Right? So these Mach numbers are possible only for re-entry vehicles from space. Right? When the spacecraft enters the Earth's atmosphere from space, so its Mach number will be around 25 to 30 Mach number. Right? So it means that the spacecraft is moving 25 times the speed of sound at that atmospheric temperature. Right? The speed of sound is not at sea level, the speed of sound is at the atmospheric altitude at which the spacecraft is entering. We'll move on to discuss the types of drag. So there are various types of drag when you talk about generating a resultant aerodynamic force. Let's discuss the types of drag one by one. So first we have skin friction drag. Now this drag is due to the frictional stresses developed. Frictional stress is nothing but the shear stress developed due to the integration of the surface. Right? So this is called as skin friction drag. Then I have pressure drag. It is a drag due to the pressure imbalance in the drag direction caused by flow separation. So in the previous lecture we have discussed what is flow separation, how it happens, why it happens. So when the drag builds up because of flow separation, then that type of drag is called as pressure drag. Moving on to the next drag, that is profile drag. This profile drag is the sum of skin friction drag and the pressure drag. So if I combine both the skin friction as well as the pressure drag, that drag is called as the profile drag. Next important drag is the interference drag. It is the additional pressure drag caused by the mutual interaction of flow fields around each component of the airplane. Now when I individually test the components like the airfoil, the fuselage separately, I get a different drag. Let's say if I want to give a number, let's say 0.05 is the drag generated by an individual airfoil or wing. When the same wing is attached to the fuselage, and then if we try to identify the drag, we get more than 0.05. Now this kind of drag is called as interference drag. It has been developed due to the interaction between wing and fuselage in this case. Now if I keep on adding components like engine, horizontal tailplane, vertical tailplane to the fuselage, the net increment in drag due to the interference of these components is much higher. Moving on to the next drag, that is the parasite drag. Now this drag, we define it for the complete airplane, whereas profile drag we have defined only for particular component, let's say for wing or for the fuselage. So parasite drag is the profile drag if defined for the complete aircraft. Moving on, we have very important drag called as induced drag. Now most of you have heard about it. Let's discuss what it is. When I talk about a 3D wing, we have discussed the different types of wings when we discuss the wing plan form geometry. What are the types of wings we have? We have 2D wing as well as 3D wing. 2D wing where the span varies from -infinity to +infinity, whereas a 3D wing has got a finite span. When I talk about 3D wing, when I say 3D, that means the air can flow in all the three directions across the particular wing. Now, in 3D wing, what happens? Air on the lower surface of the wing will be at high pressure. Air on the upper surface of the wing will be at low pressure. Because the tip exists, the air at the wing tip from the lower surface tries to move towards upper surface only at the tips. Now when this process goes on, and as the wing moves further in the atmosphere, we get something called as wingtip vortices, which leaves from the trailing edge. This wingtip vortices reduces the angle at which the incoming air is coming and hitting the leading edge. Now this effect is called as induced effect. Because the angle is reduced, the lift developed will be reduced. Similarly, drag will increase. Now this increment of drag due to lift, this is called as induced drag. We also call induced drag as lift dependent drag. Moving on to the next type of drag, that is zero lift drag. It is a drag that exists when the airplane is at its zero lift angle of attack. So zero lift drag is nothing but a parasite drag, which means I don't want the drag, but it still exists because of the components. So that is zero lift drag. And then we have a drag due to lift. Any drag measured above the zero lift drag, we call it as drag due to lift or induced drag. I would like to introduce a new concept called as critical Mach number. Mach number, all of us know, it is the ratio of the velocity of an object to the velocity of sound in that medium. So that is Mach number. If I travel at a Mach number of 1, that means I am traveling at speed of sound in that medium, right? When I say in that medium, that means with respect to the temperature in that medium. Why? Because the speed of sound depends on temperature. In this particular figure, diagram A represents a cambered airfoil which is at a free stream Mach number of 0.3. Now, as the air starts to move on the upper surface of the airfoil, it starts accelerating, right? Because there is a bend and the air has to take a turn, the flow starts to accelerate up to certain point, let's say 40% of the chord. Now, because of this acceleration, the Mach number, the local Mach number on the surface of the airfoil at any point, let's say it reaches to 0.435. Free stream Mach number is 0.3, whereas the local Mach number is 0.43, right? I still increase the free stream Mach number to 0.5, where I could able to see the local Mach number going to 0.7. Now, if I keep on doing this, when I reach a particular Mach number, or that is the free stream Mach number, when the Mach number on the surface of the airfoil reaches Mach 1, that free stream Mach number is called as critical Mach number. So what is a critical Mach number? A critical Mach number is the free stream Mach number for which the local Mach number on the airfoil surface reaches sonic condition. That Mach number is called as critical Mach number. So for in this example, the 0.61 is the critical Mach number. Moving on to the next discussion, which is in continuation with the previous one, that is the critical pressure coefficient. So critical Mach number, we have understood, it is a Mach number at which the local Mach number reaches sonic condition. Now, critical pressure coefficient is the pressure coefficient at critical Mach number. The corresponding pressure coefficient for critical Mach number is called as critical pressure coefficient. In other words, the critical pressure coefficient is a point at which the local flow reaches sonic condition, or the pressure will be at its minimum on the surface of the airfoil, whether it is upper or lower surface. In most of the cases, it is on the upper surface, because lower surface we have designed in such a way that the acceleration will be minimum, or the change in velocity or pressure is minimum. So that is why it is most probably on the upper surface. Since we are discussing about different types of drag, it is very important to understand the effect of drag on the Mach number. Right? If you can see the graph, we have points A, B and C corresponding to the free stream velocities that is shown on the right hand side with three figures A, B and C. At A, the free stream Mach number is less than critical Mach number. Right? That means nowhere on the surface of the airfoil the flow has reached sonic condition. Figure B represents the free stream Mach number greater than critical Mach number, but it is less than some other Mach number. We will discuss what that Mach number is. But because the free stream Mach number is greater than critical Mach number, there exists a region on the airfoil surface where the Mach number is greater than 1, right? So it is clearly shown that area in figure B. Now if I still exceed the Mach number more than the drag divergence Mach number, then that Mach number results in the generation of shock waves. Let's rewind a little bit. Let's move on to point B. Now point B is a point in this particular graph of CD versus Mach number with very little increment in Mach number. The coefficient of drag drastically rises. Now this point is defined as the drag divergence Mach number, and it occurs nearer to the transonic region where there is a possibility of generation of shock waves. So the Mach number at which the drag drastically increases, that Mach number is called as drag divergence Mach number. If I still increase the Mach number beyond the drag divergence Mach number, definitely there will be shock waves on the airfoil surface.